Today we're going to look at some examples of uniform circular motion. We're going to look at a simple pendulum example and a roller coaster problem example. So let's just quickly remind ourselves, if we have something uniform circular motion, means it's moving in a circular path at a constant speed. And anything that it's undergoing uniform circular motion has an acceleration towards the center, we call it a centripetal acceleration, that is equal to v squared over r. Now we could also say that the centripetal acceleration is equal to omega squared times r, the angular velocity squared times the radius. They're saying the same thing. We also remember that net force acting on an object is equal to mass times acceleration. Therefore, if we have something undergoing uniform circular motion, the net force would equal mass times v squared over r, or mv squared over r. So these are kind of some of our basic equations. Now let's take a look at a simple pendulum situation. So for this simple pendulum, I'm going to consider it's swinging in an arc, something like this. So we can see that it is in fact in circular motion, but it is not uniform circular motion because the velocity is changing. So because the velocity is changing, we need to look at something, in this case, for example, let's look at energy. So energy initial equals energy final, and so the energy, say here at the top, equals the energy at the bottom. At the top we have gravitational energy, mgh, and at the bottom we have kinetic energy, 1/2 mv squared, h being, of course, the distance from here to here. That's h. So mgh equals 1/2 mv squared. If we solve this for v, we can cancel out the m's, multiply by 2, take the square root. The square root of 2gh is v. So that's how fast the pendulum bob is moving at the bottom of its path as it's swinging back and forth like this. So that's our speed. Now, suppose a question said, what is the tension in the string when it's at the lowest point? So the tension in the string at the lowest point, we would begin by drawing a force diagram. And so here at the lowest point, we know there's a force of gravity down equal to mg, and there is a tension force up. And because it's moving in a circular path, I know that it's accelerating towards the center, which means that the tension force has to be bigger than mg. So here I'm going to take net force equals mass times acceleration. The net force, because it's accelerating up, is going to be T minus mg. That will equal m times a. In this case, m times v squared over r. So the tension is going to equal mg plus mv squared over r, just adding the mg to both sides. And because the v, because of energy, we found the v was the square root of 2gh, we could do this. The tension is equal to mg plus m v squared over r. V squared, v being the square root of 2gh, I square it, just gets rid of the square root. So m times 2gh over r. So this is our tension. So if we had a mass and a radius, and the height change here, we would be able to figure out what the tension is. So symbolically, this would be our tension. We could write this if we wanted to, factor out mg, then we'd have 1 plus 2h over r, but we wouldn't need to go that far. This far would be sufficient. That is the tension of the pendulum bob at the bottom of its swing. Now let's look at a roller coaster problem. So suppose we have a kind of a simple roller coaster here. This is radius r, and we start the coaster up here at a height h above the ground here. And we've got the roller coaster, it's going to be released from rest, frictionless slide, zip around this little loop-to-loop and come back here. So a couple of things about roller coaster problems like this. So at the top, okay, we've got the mg force, force of gravity, downward. And if there is a normal force, it's going to be perpendicular to the track at this point, which means it would also be downward. So at the top, our net force is going to be mg plus the normal force, if there's any normal force there. At the bottom, mg normal force, and because it's moving in a circle, at the bottom it's accelerating towards the center. At the top it would also be accelerating towards the center. So at the bottom, our net force is going to be normal minus mg. So as I look at this, at the top I could set F equals ma, so I could say mg plus normal equals m times velocity at the top squared over r. Whereas at the bottom, I would say normal minus mg equals m times velocity at the bottom squared over r. So let's suppose that we're moving just fast enough that the cart is not going to lose, well, it's going to barely lose contact with the track, but it will maintain its circular path. At the smallest possible speed at the top at which that will occur is the speed at which the normal force drops to 0. The faster we're going, that's fine, the more the normal force would be. But if we go too slow, it's going to lose contact with the track and it's just going to fall. So if we're going at just the right speed, then it's going to be just barely losing contact, but just have enough to keep maintaining its circular path. So when the normal force shrinks to 0. So then I have the situation mg equals mv the top squared over r. Mass will cancel out, and I can see that velocity at the top is going to be the square root of gr. That's the minimum speed at the top at which it will continue its circular path without falling. So there's my speed at the top. Now my speed at the bottom, let's say the question says, you know, how high must I drop this so that it's going to be able to go through the loop-to-loop and reach the top with just the right speed? Well, if I'm looking at that energy problem, energy initial equals energy final. So the initial energy here, I've got mgh. That's going to equal the final energy. If I'm looking here at the top, that's going to be 1/2 mass velocity at the top squared. That's the kinetic energy, plus the gravitational energy here, mg, times the height here, which is equal to double the radius, times 2r. So at this point, I can see that the mass will divide out of each of these. I can also replace this top velocity, because if it's going to reach the top with just the right velocity, this is the right velocity, square root of gr. So I'm going to divide out the mass, so I get g times h equals 1/2 velocity at the top squared, that's just gr, plus, divided out the mass, so I have 2gr, right? So if I want to find out what height that's going to be, oh, look at this. I can divide out the g. So the height that I need is 1/2 r plus 2r. And that's going to give me an initial height of 2.5 r, or 5/2 r. So releasing from that height on this frictionless ramp will allow it to reach the top with just the right velocity. So what would be the velocity at the bottom then? Well, velocity at the bottom, I would do energy initial equals energy, we'll say at the bottom this time. So what I have is mgh, that's mg times 5/2 r, equals the energy at the bottom. At the bottom, it's at the ground level, so all of the energy is kinetic. 1/2 m velocity at the bottom squared. So here I can divide out the mass, and I've got, so let's see, let's call this 5/2 gr equals 1/2 velocity at the bottom squared. I can multiply everything by 2, and then I can take the square root. So the square root of 5gr, lowercase there, is equal to the velocity at the bottom. So we found the velocity at the bottom. Now suppose a question said, what is the normal force at the bottom? Well, at the bottom, for finding the normal force, here I am. At the bottom, the normal force is, the net force is normal minus mg. So normal minus mg equals mv bottom squared over r. So normal will equal mg plus m v bottom squared. So I square the square root, gets rid of it, so I got 5gr over r. So the over r, notice the r's will cancel. What I've got is mg plus 5mg. So the normal force at the bottom is going to be 6mg. So if there were a scale at the bottom, the normal force, remember, measures what the scale would say. It would read on the scale that you weigh 6 times your actual weight. So that's how fast you're moving, that fast in this loop-to-loop problem. Hope this gives you a better idea of how to solve some of the circular motion problems, especially those involving, we've got forces here, we've got energy, and there you go.